A photo surfaces from an unlikely source, not from ESA, not from NASA, but from a backyard in Finland. The image shows something we've never seen in a comet. A forward-facing structure, a beam of light where there should be none, and a shadow tucked just beneath the solar glare. This is 3I Atlas, an interstellar object behaving as if it's aware of us. The official channels have gone quiet, but the amateur community hasn't. They're watching, photographing, tracking, and one frame at a time, they're building the strangest story in modern astronomy. If you're listening right now, mark your exact time and location in the comments. We're mapping the watchers of this mystery. And if you believe truth should not wait for a press release, subscribe and stay until the end. Now, let's begin. It wasn't supposed to begin this way. No press release. No grand discovery from a billion-dollar observatory. Just a quiet frame, uploaded from the edge of a forest in Finland, taken by someone most of us will never meet. The time was 1642 UTC. The date, October 23rd, 2025. And what that frame revealed, intentionally or not, would trigger the most unsettling week in recent astronomical memory. The equipment wasn't special. A solar-modified Newtonian telescope, mid-range optics, a hobbyist's mount. But the astronomer behind the camera had one thing most institutions didn't, the will to point it straight at the sun when everyone else had stopped looking. Solar conjunction, they said, made it impossible to observe anything near that region. The glare would overpower the sensors. Risky, ill-advised, a waste of time. But that one frame said otherwise. When the photo was first posted online, it didn't immediately scream anomaly. It showed exactly what one might expect when aiming a scope toward the sun's outer boundary. A haze of scattered photons, solar interference, and faint textures layered across the glow. But something in the middle felt off. Not in color, not in brightness, in geometry. A dark wedge, almost invisible unless you knew where to look, was carved into the center left of the image. At first glance, it could have been a dust smudge, or a cooling shadow across the lens, but closer inspection told another story. This wedge had clean edges. The shape narrowed into a perfect point, aligned in such a way that it appeared to hover not on the surface of the sun, but somewhere in front of it. And more strangely, it seemed to move. That's what triggered the reanalysis. The amateur astronomer, username Dobsonian Power, had taken a series of bracketed exposures to manage the sun's intensity. By aligning those frames side by side, other observers noticed the shadow wasn't fixed. It shifted slightly between shots, not like glare, not like a sensor issue, but like an object in motion. And then came the second frame, this one from a different observer, nearly 1,200 kilometers away, using a completely different telescope. Same timestamp, same angle, same triangular void. Now, it couldn't be dismissed as lens defect or atmospheric disturbance. Now, it was real. Within hours, the image had gone viral across the amateur astronomy forums. Analysts began stacking exposures, subtracting light, isolating wavelengths, and every method pointed to the same unsettling truth. Something opaque had passed in front of the coma of 3I Atlas, something dense enough to block light, sharp enough to cast form, and slow enough to be caught mid-motion. To understand why this mattered, you have to understand how comets behave. At this point in its trajectory, just days from perihelion, 3I Atlas should have been radiating wildly. The coma, the cloud of gas and dust that surrounds every cometary nucleus, should have been massive, chaotic, and bright. There should have been no hard edges, no voids. Just turbulence. But this wasn't turbulence, it was silence. What this single frame captured wasn't just a moment in time. It was a contradiction, a structure where there should be randomness, a shape where there should be fog, and more than anything, a motion that didn't fit the physics we expected. At first, the mainstream ignored it. No statements from ESA, no response from NASA, but privately, forums started lighting up with another kind of speculation. Could it be a fragment, a companion object? Or something not natural at all? No one knew, but what everyone agreed on was this. From the moment this image surfaced, 3I Atlas was no longer just a comet. It had become a question, and that shadow, whatever it was, had just crossed the threshold between speculation and evidence. Every comet carries a halo, a veil of dust and gas, called the coma. It's what makes them visible in the first place. When sunlight strikes an icy nucleus, the surface begins to sublimate, frozen carbon dioxide, methane, and water vapor escaping directly into space. These gases drag microscopic grains of dust along with them, forming a bright, hazy envelope that expands thousands of kilometers in every direction. The process is chaotic, violent, and beautifully predictable. But 3I Atlas has never behaved like anything we would call predictable. When the first high-exposure photographs were released by independent astronomers, everyone expected to see a glowing sphere of activity. Instead, the coma appeared divided patches of light and darkness, alternating like waves under a hidden pattern. At first, the variations looked subtle, but as more data came in, one feature became impossible to ignore. Sections of the coma were darker, sharply defined, and eerily consistent from frame to frame. They weren't random fluctuations, they were shadows. In space, that word carries weight. A shadow requires structure, a barrier that blocks light, a geometry that resists scattering. But a comet's coma isn't solid. It's a diffuse cloud, constantly shifting. Nothing inside it should cast a fixed shadow. And yet, every frame showed the same phenomenon. Narrow corridors of dimness, cutting through the glow, always aligned along the same axis as the object's motion. Researchers scrambled for natural explanations. Some proposed that 3I Atlas was venting gas through narrow jets, creating denser filaments that looked like dark veins within the coma. That would make sense if those jets were rotating, pulsing, or dispersing. But they weren't. They stayed perfectly still relative to the nucleus. Even when the object moved closer to the sun and the solar wind intensified, the shadows remained locked in place. To understand how strange that is, imagine a cloud of steam rising from a boiling pot, and instead of swirling freely, the vapor forms straight, unwavering lines that never break apart. That's what astronomers were seeing through their telescopes. A fluid behaving like a framework. A second anomaly soon followed. Spectral analysis of the dimmed regions showed an unexpected absorption pattern. Light passing through those darker lanes wasn't merely being reduced, it was being filtered, as though it had passed through a thin layer of material. Certain wavelengths vanished completely, particularly in the green band associated with diatomic carbon emissions. Something inside the coma was selectively absorbing light. That discovery sent ripples through the community. Could it be mineral dust? Metallic compounds? Even magnetic interference from charged particles? Each hypothesis had holes. Dust particles scatter, not absorb. Magnetic fields fluctuate. They don't create sharp boundaries. Whatever was happening around 3I Atlas was maintaining shape, density, and orientation with uncanny precision. As more amateur astronomers joined the effort, stacked images from multiple nights confirmed it. The same shadow structure persisted, shifting only slightly as the comet's angle to the sun changed. A few even reported seeing faint luminosity inside the dark regions like threads of light moving within the shadow itself. That shouldn't happen either. Some called it an optical illusion. Others whispered the word structure, not because they wanted to believe in something artificial, but because no natural model seemed to fit. For the first time, professional observatories quietly began cross-checking their own archival data. They found traces of the same dimming pattern weeks earlier buried in calibration frames that had been dismissed as noise. The phenomenon wasn't new. It had simply gone unnoticed. So what were these shadows? Condensed plumes frozen in alignment? Magnetic filaments shaped by solar wind? Or something that required an entirely different vocabulary, an interior, a design, a mechanism? No one had the answer, but one fact was now certain. 3I Atlas was not surrounded by a random coma of dust. It was surrounded by a patterned field, an organized shell, where light obeyed rules we didn't write. And in that silence between brightness and absence, the comet seemed to be hiding something, a secret written not in light, but in the shadows that refused to move. The human brain is wired to see shapes. It's how we navigate the world: patterns in the stars, faces in the clouds, meaning in randomness. But every now and then, something appears that doesn't ask for interpretation. It simply is. and once you've seen it, you can't unsee it. That's exactly what happened on October 24th, 2025. It began with a live stream. An amateur solar observer known online as Chris Green was using a Herschel wedge to observe the sun's photosphere. His setup was modest: a refractor telescope, standard white light filter, and a tracking mount. He wasn't hunting for mysteries, he was simply trying to view sunspots. But as he adjusted his exposure, he noticed something strange hovering near the edge of the disk. It was dark, sharp, angular. He captured a series of frames, paused the session, and uploaded one image to a small astronomy forum. The caption was simple: "Does anyone else see this triangle?" At first, the responses were skeptical. Dust on the lens? Dead pixels? A camera artifact? But then something unexpected happened. Another user observing from a different continent, using different equipment, posted an almost identical image. Same triangle, same position, same angle. That changed everything. In the image, the triangle doesn't appear faint or fuzzy. It's not a smear or an arc. It is precise. 3 edges, 3 clean points. It casts no visible flare, and yet it absorbs the background light completely. Where the sun's glow should be strongest, there is absence not just of brightness, but of signal. Solar physicists were quick to run through the checklist. Could this be a filament, a prominence, a coronal cavity? None of them fit. Prominences are fluid and looping. Filaments appear wispy and irregular. But this was none of those things. It was geometric, and it was stable. Over the course of 3 hours, observers tracked the triangle's relative position. It didn't drift like a solar flare. It didn't oscillate like a floating dust mote. It held its orientation, moving slowly, as if part of something larger, something in controlled motion across the face of the Sunday. That's when the triangulation began. Amateur astronomers across the northern hemisphere began capturing their own images. And in those who had the right angle, the triangle was there. Not always identical in scale, sometimes rotated, sometimes slightly offset, but unmistakably present. The phenomenon wasn't tied to one camera or one observer. It was spatial, real. Now the community was faced with a question no one wanted to ask out loud. Was this object part of 3i Atlas? The timing made it hard to ignore. The triangular anomaly appeared precisely in the region where 3i Atlas had been last observed just days before it entered solar conjunction. Trajectory maps from the Jet Propulsion Laboratory confirmed the overlap. The object was moving through that exact corridor at the time of the triangle's appearance. And then came a more unsettling possibility. What if this wasn't a piece of 3i Atlas, but a companion to it? Some speculated that the triangle was a probe, a smaller body deployed from the main object, hovering near the sun for a specific purpose. One theory suggested energy harvesting. Another, trajectory correction via solar gravity mapping. The most conservative explanation proposed it was simply a fragment, a shard of ice or rock, behaving unusually due to shape or spin, but none of those hypotheses accounted for the sharpness, the consistency, the way the light folded around it. What was most disturbing wasn't the shape itself. It was what it implied: intention. If this object was natural, then it was unlike any fragment we've ever observed near a star. If it was artificial, then it wasn't just observing, it was acting. And as quickly as it appeared, the triangle vanished. No flares, no breakup, just gone into the blinding light of the Sunday. We may never see it again, but in that one perfect moment, captured by ordinary people with extraordinary timing, we saw something near the sun that didn't belong there, and it pointed not just to the mystery of 3i Atlas, but to the possibility that something else was moving with it. At first, it was dismissed as noise, a minor fluctuation in brightness, buried inside a blurry green haze. The kind of anomaly that gets filtered out in the early stages of image processing, not because it's unimportant, but because it's assumed to be meaningless. A flicker in the exposure, a calibration issue, a passing shadow. But this time, it didn't disappear. It came back, again, and again, and again. The pulse was first noticed in a stacked long-exposure image taken by a deep-sky observer in southern Chile. He wasn't tracking 3i Atlas directly, not at first. He was running high-sensitivity CCD tests on diffuse light sources, trying to isolate atmospheric distortion patterns near the solar limb. But when he cleaned the images and adjusted contrast in the green channel, where cometary emissions are often strongest, he saw something peculiar. A wave. A soft, symmetrical brightening in the coma of 3I Atlas. Then darkness. Then light again. Every 11.2 hours. He assumed it was an error in stacking, perhaps a misalignment of frames. But when he looked at the raw images individually, the pulse was still there. Faint, but real. Out of curiosity, he passed the data to a colleague at Las Campanas Observatory. Within days, it had been independently confirmed using entirely different equipment, and when the signal appeared again, this time in the infrared range, the mystery deepened. The pulse was not optical. It was not a surface reflection. It was emitting from within. To be clear, variability in comet brightness is not uncommon. As they rotate, comets expose different surface areas to sunlight, triggering uneven outgassing and asymmetric reflection. Bright regions flare, darker ones dim. But those changes are chaotic, irregular. No natural comet, in any archive or mission record, has ever demonstrated a precise periodic pulse like this one. The consistency was mathematical, every 11.2 hours, within a margin of error less than 0.01%. No drift, no decay, just a clean, repeating signal. The next step was spectral analysis. Teams from 3 continents began reprocessing earlier observations of 3I Atlas using time-lapse photometry. They weren't looking for brightness now, they were watching how the brightness moved, and what they found was striking. The pulse didn't just brighten the coma, it expanded it. Each wave of energy was accompanied by a visible increase in coma radius, a soft outward bloom, followed by a gentle contraction. The motion wasn't turbulent or explosive, it was almost biological, like breathing. Now, a new question emerged. Was the nucleus of 3I Atlas reacting to sunlight or responding to something else? Some suggested deep thermal resonance. In theory, a comet with internal pressure gradients might exhibit oscillating stress, causing periodic release of trapped gases. But this didn't match the thermal models. The inner core temperature of 3I Atlas, as observed by the James Webb Space Telescope, was too low for rapid phase change, and no jets were visible, no vents, just light pulsing through dust like a heartbeat in fog. What made it stranger was the harmony. Every fifth pulse, precisely at the 56-hour mark, included a secondary ripple, a microflare that appeared between 2 full peaks. It was a pattern within a pattern, a harmonic signature. That kind of coherence doesn't arise by accident. At this point, some researchers began to use a different term, signal, not because it was encoded, not because it carried information, but because it acted like something controlled, something timed. It's possible, of course, that this is all natural, an exotic interaction between radiation and dust, filtered through a coma unlike any we've seen before. But even that would make 3I Atlas the first of its kind. A comet that pulses, that breathes, that holds rhythm in vacuum, and until we understand what's driving it, we cannot say for certain whether it is the product of physics or something with memory. If the pulse had been isolated, a flicker in one telescope, a rhythm buried in one dataset, the explanation would have been easy. Anomaly. A localized distortion. Perhaps an instrumental quirk or a calibration oversight. But that's not what happened. Instead, it began to synchronize. The same 11.2-hour pulse observed in Chile soon appeared in other data streams, first in the infrared range, then in the ultraviolet. Different instruments, different wavelengths, different hemispheres, all detecting the same rhythm, from the same object, with the same stability. That's when it stopped being a flicker, and started becoming a problem. The European Space Agency's calibration team ran a side-by-side comparison of spectral readings from 2 satellites, one in Earth orbit and another positioned near the Lagrange point. These satellites were hundreds of thousands of kilometers apart with different detectors, different solar angles, and different data pipelines. And yet, when they plotted brightness against time, the 2 graphs aligned, precisely. Every peak, every trough, every fifth harmonic. The pulse wasn't just repeating, it was phase-locked across space. That should be impossible. In standard comet physics, light variation is caused by outgassing. Dust, vapor, or gas is ejected from the nucleus when sunlight hits volatile material. These emissions are messy. They flicker, rotate, surge, and decay. They do not coordinate with outside observers. They do not hold phase in multiple wavelengths, and they certainly don't match up across planetary distances. But 3I Atlas was doing exactly that. At first, astronomers thought it might be a rotational signal. Perhaps the nucleus had a hotspot, a reflective patch that spun into view every 11.2 hours. That could explain the light curve. But then the thermal data came in. The James Webb Space Telescope detected the pulse as well, not just in brightness but in temperature. Every 11.2 hours, the surface of the coma rose slightly in infrared emission by roughly 2.4%. The rise was gentle, predictable, and it originated not from a rotating patch but from within. This suggested something more than surface reflection. It suggested internal coordination. Now the model began to crack. In November, a new layer was added when the Atacama Large Millimeter Array, one of the most sensitive radio observatories on Earth, detected a periodic frequency disturbance originating from the same sky region. It wasn't a signal, not in the traditional sense, but it was a pattern. A low-level electromagnetic fluctuation that rose and fell every 11.2 hours. This convergence across optical, thermal, and electromagnetic bands left scientists with two possibilities. Either every instrument was wrong in exactly the same way, or 3I Atlas was doing something comets aren't supposed to do. The synchronization problem deepened when amateur astronomers began noticing something stranger. The pulse seemed to correct itself. If a small deviation occurred, if one peak arrived a few minutes early, the next cycle would compensate. The waveform recentered. It held its timing like a metronome, adapting. That's not just repetition, that's feedback. Natural systems can resonate, but they don't self-correct. They don't hold time across multiple observation points. They don't synchronize across the electromagnetic spectrum. That behavior belongs to systems with control mechanisms, mechanical, computational, or biological. Still, no one could say for sure what was causing it. Was it internal, pressure modulation, resonant sublimation, something else entirely? All we know is this. A non-spherical interstellar object currently beyond the reach of most direct observation is maintaining a precise timed energy pulse across light, heat, and field, and it's doing so while on an inbound trajectory through our solar system. If this were a satellite, we'd call it a beacon. If it were biological, we'd call it a heartbeat. But it's neither. It's a comet that behaves like a clock, and the deeper we look, the more we realize we're not just observing 3I Atlas, we're syncing to it. In astrophysics, there are certain pairings we come to expect: hydrogen and helium, carbon and oxygen, nickel and iron. They are cosmological twins forged together in the cores of massive stars, ejected into space during supernovae, and scattered across galaxies as raw material for planets, moons, and comets. Wherever one appears, the other follows. It's not just probable, it's elemental logic. These metals condense together. They bind together. They travel through cosmic time together. But not this time. When the European Southern Observatory published its first high-resolution spectrographic pass of 3I Atlas, something strange stood out. Nickel. Bright. Isolated. Ionized. The spectral lines weren't subtle. They were clean, sharp, and undeniably present, indicating both neutral and singly ionized nickel atoms drifting in the gas around the object. That in itself wasn't shocking. Nickel is found in many comets, though usually in trace amounts, locked within mineral dust. But what followed was harder to explain. There was no iron, not faint, not blended, not hidden beneath the noise floor. Absent. The two iron signatures that should have appeared Fe1 and Fe2 were missing. Repeated scans confirmed the absence. At first, the team suspected an equipment fault, so they recalibrated. Then cross-checked against a known iron-rich asteroid for comparison. Still nothing. The anomaly held. Then came confirmation from the Gemini South Telescope in Chile. Different hemisphere. Different instrument. Same result. Nickel. Without iron. That shouldn't happen. Not in nature. Not on this scale. The first explanation proposed was selective sublimation. Perhaps nickel was being preferentially released from the nucleus due to unusual thermal properties leaving iron behind. But lab models showed no known surface chemistry that could vaporize nickel at the observed temperatures while suppressing iron to zero detection. Their vaporization points are close, their bonding affinities are similar. If one appears, the other should trail close behind. Another theory was geological sorting. The idea that three eye atlas originated from a parent body where iron and nickel had separated over time due to gravity or impact processes. That explanation works for planetary cores, but not for small icy objects wandering between stars. There's simply not enough time, heat, or pressure to pull apart these two tightly linked metals. So the question became unavoidable. What kind of process could isolate nickel from iron and release it in gas form into space? Only one answer remained: refinement. On Earth, nickel is extracted through high-temperature industrial processes, smelting, electrolysis, or chemical leaching. All of them involve energy. All of them involve purpose. In those systems, iron is typically removed first as slag or waste. The result is purified nickel, often used in electronics, alloys, or radiation-resistant shielding. That's what the spectroscopy now resembled, not mineral chaos, but material selection. Some scientists hesitated to use the word, others didn't. A confidential memo from a Japanese lab later leaked described the signal as consistent with post-processing metallurgy. Not just that nickel was present, but that it was clean. Even more concerning was the distribution pattern. The nickel wasn't clumped. It was drifting in a symmetrical arc along the object's coma, forming a ridge of vapor that appeared to pulse in sync with the 11.2-hour cycle already observed in light and heat. That changed the framing. This wasn't just an anomaly. It was part of the system behavior of 3I Atlas, a metal signature, in motion, coordinated with the energy rhythm. At that point, the standard models began to fold. No known comet carries vaporized, purified nickel in isolation. No natural body emits synchronized pulses of refined material. The data now suggested something few dared to say out loud. If 3I Atlas isn't a natural object, then what we're detecting may not be a composition. It may be a construction, not built by us, not for us, but unmistakably shaped by intention. On paper, the European Space Agency is one of the most transparent scientific institutions in the world. Its data repositories are open access. Its telemetry feeds are public. Its missions from Rosetta to Gaia have helped rewrite entire chapters of modern astrophysics. But in late October 2025, something changed. It began subtly. The public ephemeris files tracking 3I Atlas previously updated daily stopped refreshing. Then, high-resolution imaging archives from the Mars Trace Gas Orbiter were delayed. These weren't system outages. The servers were live. Other datasets continued to flow. Only one object, in one corridor of the solar system, had gone dark: 3I Atlas. Observers noticed, amateurs and professionals alike. The object had just passed within 0.04 AU of Mars, an extraordinarily close flyby, visible to multiple ESA instruments, including TGO, ExoMars, and even Earth-based tracking arrays. By all metrics, this should have been a rich window for science. A surge of new data, detailed spectroscopy, imaging, time-lapse motion tracking. Instead, there was silence. And not technical silence. Administrative silence. ESA spokespeople cited instrument prioritization and data backlog. They pointed to the ongoing solar conjunction, reminding the public that observations near the Sun are inherently difficult. But those explanations didn't hold. Solar conjunction affects Earth-based visibility, not spaceborne cameras already positioned beyond the solar limb, and no other datasets from nearby instruments showed similar disruption. What made the silence louder was its timing. Just hours before the data flow halted, 3I Atlas had begun exhibiting measurable deviations in its trajectory. Slight, but statistically significant. Amateur astronomers cross-checking orbital predictions from JPL's Horizon system noticed that the object's outbound vector had been adjusted. A minor course correction, unexplained, shifting the comet's future path by tenths of a degree. Again, no comment, no bulletin, just metadata updates, silently pushed through back-end channels. Then came the internal classification change. On ESA's object tracking server, a technical portal rarely visited by the public, 3I Atlas's designation was quietly altered. It was no longer labelled as an interstellar transient. Instead, it now appeared as a capture candidate, pending orbital confirmation. No blog post, no public-facing update. The change lived only in the metadata, where only institutional researchers were likely to notice it. But some did, and they asked, why? Capture candidates are rare. For an object on a hyperbolic path entering our solar system at escape velocity to suddenly begin curving inward suggests a significant loss of kinetic energy. In natural terms, that would require either a major outgassing event or a gravitational encounter. Yet ESA had released no observation of such an event. No plumes, no jets, no visual or thermal trigger. And still, the data feed remained quiet. That silence stood in stark contrast to earlier behavior. In the past, ESA has broadcast even minor comet outbursts in near real time. When Comet Borisov showed signs of fragmenting, updates were released within hours. When Rosetta's lander Philae lost power, the public was informed immediately. But with 3I Atlas, one of only 3 confirmed interstellar objects ever recorded, the agency had gone opaque. So observers began comparing timestamps. The last full-resolution image released from ExoMars, October 17th. The last confirmed trajectory update from the public API, October 20th. The moment the silence began, the same day amateur astronomers photographed the triangular anomaly near the sunday. Was it coincidence? Perhaps, but the silence itself became a signal, because in science, patterns matter. And a deviation without disclosure isn't just an omission, it's a message. A message that says, this object is no longer being treated like a comet. This object may no longer be just science. And for the first time in this story, what we weren't told became more revealing than what we were. Jets are normal. They're what we expect from a comet as it approaches the sunday. As sunlight heats the nucleus, volatile ices begin to sublimate, shifting straight from solid to gas. This gas escapes through fissures and vents, carrying dust and particles with it. The result? Narrow columns of material shooting into space, forming the familiar hazy tail that follows the comet's path. It's messy, chaotic, a direct consequence of heat meeting ice. That's how it's supposed to work. But 3I Atlas didn't follow the rules. When high-zoom imaging from the Daniel K. Inouye Solar Telescope in Hawaii was analysed in late October, a team of planetary scientists noticed something odd. The jets emanating from 3I Atlas weren't spraying randomly across the surface. They weren't even rotating with the nucleus. Instead, they were locked in place, fixed in orientation, like thrusters on a stabilized platform. This contradicted everything we know about natural jet behavior. Typically, as a comet spins, its vents rotate into and out of sunlight. Jets flicker on and off, depending on temperature, angle, and surface shadow. Even large active comets like 67P tracked in detail by ESA's Rosetta mission display complex swirling plumes that change hour by hour. But 3I Atlas's jets didn't change. They fired in the same direction, at the same intervals, with nearly identical brightness curves, synchronized with the 11.2-hour pulse we'd seen earlier. Even more strangely, the jets didn't match the expected axis of rotation. Instead of radiating from the nucleus like spokes on a wheel, they seemed offset, emerging from angles inconsistent with any known spin model. In fact, when backtracked across multiple observation points, the jets appeared to curve, not as a result of solar wind, not from gravitational drag, but as if they were steering. That single word steering changed the nature of the conversation. For a jet to steer an object in space, 3 conditions must be met. It must emit directionally. It must maintain consistency over time. It must induce observable changes in velocity or orientation. 3I Atlas met all 3. Between October 18 and 24, subtle shifts in its outbound trajectory were recorded. At first, they were thought to be measurement noise. But as the same pattern repeated, telemetry analysts began to reconsider. The object wasn't just drifting. It was accelerating by micro-increments in a direction aligned with the dominant jet vector. This type of behavior is unheard of in natural comets. Jets may nudge trajectories slightly, but always in response to solar heating. They are reactive, thermal, random. 3I Atlas appeared deliberate. The chemical analysis made things even stranger. Using combined ultraviolet and visible light spectroscopy, researchers detected a high concentration of monatomic oxygen and carbon byproducts of high-energy breakdown of CO and CO2, but without the thermal gradient expected from solar heating. Translation: the jets were hotter than the comet's own surface, by a factor of 5. The likeliest explanation? An internal heat source, not external radiation. Some suggested radioactive decay. Others, exotic chemistry under pressure. But neither theory explained the vector stability or rhythm. Because in the end, this wasn't just about temperature, it was about timing. Every time the 11.2-hour pulse peaked, the jet activity surged as if the object were pulsing and firing in lockstep. Natural bodies don't do that. Mechanical ones do. To be clear, there is no confirmed evidence that 3I Atlas is artificial, but its jets behave like something under guidance, not random, not thermal, not natural, and the closer it gets to the inner solar system, the more those jets begin to resemble maneuvers. Mars has hosted more robotic visitors than any other planet in the solar system. Its orbit is mapped in millimeters, its skies monitored by satellites, its surface scanned daily by a fleet of orbiters, landers and rovers, many of them active, transmitting and watching. So, when 3I Atlas passed within just 0.04 astronomical units of the planet, closer than any known interstellar object in history, scientists expected a data windfall. Dozens of instruments were primed, from ESA's Trace Gas Orbiter to NASA's MAVEN and Mars Reconnaissance Orbiter. Every major platform had a window on the flyby, but what we got instead was silence, and what data we eventually received didn't line up. It began on the evening of October 21st, when the object entered Mars's observational corridor, a 6-hour window where it would pass within clear line of sight of at least 3 instruments capable of spectral and imaging analysis. Anticipation was high. Even amateur astronomers tracking open feeds from Mars orbit expected confirmation shots, perhaps even high-resolution footage, but no images arrived. When questioned, ESA responded that atmospheric interference near periapsis had forced them to reallocate instrument focus. NASA, in turn, issued a vague technical bulletin referencing solar radio interference. Both agencies insisted the flyby had been tracked, just not in ways that could be made public yet. But behind the scenes, things weren't lining up. Telemetry logs from the Deep Space Network showed a 2-hour communication blackout from multiple Mars orbiters, a window that coincided precisely with the closest approach of 3I Atlas. During that gap, MAVEN's ultraviolet spectrometer recorded a spike in ionospheric activity above the planet. The magnitude of the spike suggested a foreign energy input, one that wasn't solar, wasn't magnetic, and wasn't atmospheric. It came from space. When systems came back online, orbital drift readings from 2 spacecraft had shifted. By small amounts, mere fractions of a degree, but in ways that suggested they had passed through a transient field. A force that altered their orientation just enough to trigger autocorrection protocols. Now the picture was forming. The Mars flyby hadn't just been silent, it had been disruptive. Meanwhile, on the ground, Mars surface instruments registered no seismic activity, but an unusual radio echo was detected by a passive antenna onboard China's Zhurong lander. It wasn't a transmission, not a signal, more like a shadow in the spectrum, a brief cancellation of ambient radiation, consistent with electromagnetic diffraction or deliberate signal masking. All of this should have triggered immediate international coordination, but no public interagency memo was released, no joint briefing, no flyby debrief. Instead, within 48 hours, NASA reclassified the event as a non-priority proximity pass, and the raw data logs from MRO's high-resolution camera normally posted to the planetary data system were quietly delayed. Amateur analysts watching 3I Atlas's trajectory via JPL's Horizons interface noticed something even more concerning. The object had shifted, just slightly. A deviation of 0.018 degrees from its projected outbound path. That might seem insignificant, but over interplanetary distances, it translates to hundreds of kilometers. The object had changed course. Right after Mars, no outgassing was detected. No thermal spike. No collision. Just a silent, sudden adjustment, like a vehicle correcting after passing an obstacle. And when analysts overlaid this course correction with the known geometry of Mars's magnetotail, a long, invisible sheath of charged particles stretching millions of kilometers behind the planet, they noticed something eerie. The maneuver appeared to avoid it, as if 3I Atlas knew where not to pass. Now, scientists are left with an uncomfortable sequence. A near miss with Mars, a loss of signal, a spike in ionization, a course correction, and complete silence from the most monitored planet in the solar system. That isn't just an anomaly, it's a blind spot, in a place where we were supposed to see everything. When an object enters the solar system on a hyperbolic path, it's supposed to leave. That's the definition of interstellar motion. It approaches fast, swings around the sun, and escapes forever. No capture, no return, no looping arc, unless something interferes. 3. Atlas was first catalogued as a hyperbolic interstellar object, much like Oumuamua and Borisov before it. Early estimates placed its eccentricity above 1.06, more than enough to confirm a non-bound trajectory. It was moving too fast, at too steep an angle, to ever be held by the sun's gravity. But that was before the Mars flyby, before the pulse, before the curve. In the days following its close approach to Mars, orbital analysts began to detect a subtle but consistent deviation. The object's velocity vector had changed orientation. Its outbound trajectory was no longer cleanly escaping the system. Instead, it had begun to arc not in a natural gravitational slingshot, but in a compression curve. The anomaly wasn't in the speed, it was in the angle. What became known as the capture angle was first flagged by a junior orbital modeler at ESA's Space Operations Center. Her simulation, based on updated DSN tracking points, showed that 3I Atlas was now drifting toward a zone of potential solar entrapment. Not a clean ejection, not a stable orbit, but something between the two, a parabolic bend, suggesting a slow and uneven loss of escape momentum. This should not be possible. For a comet to be captured by the sun from an interstellar path, it must lose a tremendous amount of kinetic energy, more than solar drag or planetary gravity alone can provide. A grazing flyby of Mars is not enough, not without mass loss, not without thrust, not without intent. Yet, the numbers were clear. The object was no longer outbound. It was turning in. NASA quietly updated the JPL Horizons database. The orbital eccentricity dropped from 1.06 to 1.02. Still hyperbolic, but closing. The data entry included no explanation, no footnote, just a line in code. Solution reference #53 trajectory adjusted for observed vector drift. Outside of institutional databases, amateur astronomers noticed something simpler. The object was lingering. Its apparent motion across the sky had slowed more than expected, and its predicted location began drifting away from original estimates. It was staying longer in the inner system than it should have. Then came a more uncomfortable revelation. The current trajectory would bring 3I Atlas back toward the ecliptic plane, the invisible disk on which most planets orbit. And its inclination, once steep and interstellar, was flattening. The object was aligning with us. Capture doesn't necessarily mean orbit. It doesn't mean a satellite. But it does mean change a transformation from escape to return. And if that process is happening without a visible cause, the cause may be something we're not yet equipped to detect. Some theorized that 3I Atlas had passed through an uncharted debris field. Others suggested interaction with a heliospheric plasma wave, but none of those mechanisms explain the consistency, the symmetry, or the timing, because the shift began not at random, but right after Mars. Orbital simulations now show a growing window between March and May of next year, where the object could settle into a wide eccentric loop, making it a temporary capture. That's something no interstellar object has ever done. Not in known history. If that happens, we won't be watching a visitor anymore. We'll be watching a resident, and the angle at which it enters that path, the capture angle, might tell us more about what it wants to avoid than what it wants to find. Most comets, when viewed in visible light, appear as diffuse clouds, glowing hazes of ice and dust that blur against the backdrop of stars. But shift the lens into the infrared, and a new layer of truth emerges. Infrared imaging allows astronomers to see what light obscures: thermal gradients, molecular distributions, density pockets. Inside the coma, the envelope of gas and debris that surrounds a comet's nucleus, this view often reveals asymmetric heating, jet zones, and sublimation patterns. But in the case of 3I Atlas, infrared didn't reveal chaos, it revealed structure. On October 28th, a mid-infrared imaging session from the Subaru telescope in Hawaii captured a sequence of high-contrast thermal exposures during a quiet rotation phase of 3 I-Atlas. Expecting temperature gradients to spike and fade randomly, the analysts instead observed repeating thermal contours, lines of elevated heat evenly spaced, curving around the inner coma like arcs in a magnetic field. These weren't hotspots from surface activity. They were internal bands shaped, layered, and stable. What made the finding extraordinary was that the contours weren't static. Over the course of the 11.2-hour pulse cycle, the internal structure of the coma appeared to shift, not by expanding outward, but by rotating from within, as though the heat pattern was anchored to something beneath the gas cloud. It wasn't turbulence, it was choreography. Further analysis from the Infrared Telescope Facility, IRTF, on Mauna Kea confirmed the anomaly. Narrowband thermal filters isolated multiple peaks in emission temperature, suggesting distinct, layered shells of material rotating around a core. Their spacing was not random. Each ring was separated by approximately 220 kilometers, a resonance pattern difficult to produce naturally, unless guided by a central organizing force. This was not what a coma is supposed to look like. In standard comet theory, the coma is a result of outgassing and solar interaction. Dust, vapor, and ions spill out, forming a temporary envelope that dissipates as the comet retreats from sunlight. It's unstable, uneven, driven by surface randomness. 3 I-Atlas had none of that instability. Its coma was disciplined. When overlaid with ultraviolet data from NASA's MAVEN orbiter near Mars, captured during the object's flyby, researchers found that several of the thermal arcs aligned with faint bands of ionized carbon and oxygen. Not only were the heat structures real, they were chemically distinct. One band in particular drew attention, a hollow arc forming a semicircle behind the object's path precisely aligned with the jet orientation previously detected in visible light. This arc wasn't just hotter, it reflected less starlight, indicating a denser, perhaps even metallic particulate composition. That raised a question no one could fully answer. How can a naturally occurring comet produce layered, ring-like heat zones inside its coma zones that rotate, reflect, and pulse in sync with a global rhythm? Some proposed magnetohydrodynamic forces, the interaction of charged particles with interstellar magnetic fields. Others suggested core crystallization events, triggering outward wavefronts. But neither theory accounted for the consistency. The patterns weren't fading. They weren't dispersing. They were stable, behaving less like a gas cloud, and more like a containment field. One working group, reviewing both Subaru and IRTF data, noted that the central core region assumed to be the nucleus was colder than its surrounding rings. That is not normal. In every other known comet, the nucleus is the heat source. Here, the energy was rising from the coma inward, as if something beneath the gas was absorbing, not emitting heat. It was backwards, inverted, and, unlike anything observed before, if 3 I-Atlas is just a comet, then its internal structure defies every thermodynamic model in current literature. And if it's not just a comet, then those arcs, those rings, those cold cores, may not be relics of formation. They may be components of function. For decades, radio astronomy has allowed us to hear what light cannot show. Through high-sensitivity dishes, we listen to stars, pulsars, planets, and comets. Most emit little on their own. Instead, we track how they reflect, distort, or absorb existing background signals. Cosmic microwave radiation, solar emissions, Earth-based radar pings. It's like sonar, but across the vacuum of space. So when 3 I-Atlas passed behind the Sun's limb in late October, multiple deep space antennae were instructed to monitor its passage, not visually, but through signal behavior. What came back didn't align with any previous comet profile. At exactly 3:14 UTC on October 27th, the Green Bank Telescope in West Virginia recorded a faint echo anomaly during a scheduled solar background mapping session. A low-power radio wave from Earth bouncing off the general vicinity of 3 I-Atlas returned with a phase shift. This wasn't noise, this was coherent delay, a measurable displacement in the returning wavefront's timing off by 1.08 milliseconds. At first, it was dismissed as an ionospheric irregularity common during solar activity, but other antennas in the very long baseline array, thousands of kilometers apart, registered the same distortion at the same moment across multiple frequencies. And then it happened again, exactly 11.2 hours later, matching the known pulse cycle of 3I Atlas. This time, it came not from Earth's own signal bounce, but as a distortion in the background, radiation of a pulsar positioned far beyond the object. The radio path had passed through the region of 3I Atlas's projected location, and the signal warped. There was no absorption, no blocking, just a bend-like light passing through curved glass. Radio physicists began modelling the anomaly. For a 1.08 milliseconds delay to occur at that frequency band, the radio wave must have passed through a zone of densified plasma, or an engineered field, something that could slow, scatter, or retime a radio signal while keeping its frequency intact. But there was no evidence of dust. No strong gas emission in that corridor. Nothing in standard cometary physics could account for such clean refraction. Then came the third echo. At 22:56 UTC the next day, the DSN antenna in Madrid picked up a reverse-tapered signal, a low-frequency radio return that arrived slightly ahead of the expected timestamp. That's the opposite of a delay. It indicated time compression, as if the signal had passed through a gradient that briefly accelerated part of the waveform. Multiple echoes, different shifts, all within a structured time window. By now, pattern analysts were involved. They noted that each echo occurred within a narrow phase window relative to the object's pulse, aligning with heat surges, jet emission, and even infrared structural shifts in the coma. This wasn't random scattering, it was time distortion. The most plausible natural explanation was a complex plasma shell around 3I Atlas, something with density gradients capable of affecting electromagnetic propagation. But models of this shell required an unusual assumption: a fixed field orientation. That meant the shell couldn't be tumbling freely, it had to be stabilized. Some suggested a magnetic bubble. Others speculated about supercooled ion layers. But the complexity of the refraction, especially the phase inversion, led one research group to propose something bolder: that the object was surrounded by a frequency-selective boundary. In other words, not a chaotic gas cloud, but a layer that filters specific wavelengths. Such boundaries are not unheard of in technology. We use them in stealth coatings, radio cloaks, even subspace antennas. They require control and design. If true, that would make 3I Atlas the first known interstellar object to exhibit non-random, frequency-altering behavior. Not a transmitter, not a beacon, but something even more curious. An object that listens, an object that bends signal in rhythmic sync, an object that knows it's being watched, and every echo we hear back might be more than physics. It might be the faint trace of a response. In the vacuum of space, shadows behave with perfect logic. Light travels in straight lines. When it strikes an object, the area behind that object, relative to the source, becomes dark. It's simple geometry. A comet, even one as distant and fast-moving as 3I Atlas, should follow this rule. The sun illuminates from one side. The tail extends behind. The shadow, if any, trails further still. But in a series of time-stamped amateur photos taken between October 18 and 22, a faint anomaly began to appear. It wasn't behind 3I Atlas, it was in front of it. At first, it looked like noise, a smudge in the starfield, a blur of darkened pixels just ahead of the object's vector. But image after image, from different observers across continents, showed the same pattern. A thin region of light suppression, not black, not opaque, but subtly darker, hovering just ahead of the nucleus. Some called it a photographic glitch. Others blamed local atmosphere. But then, a filtered composite image from an amateur astronomer in Argentina revealed the anomaly in clearer detail. A forward-facing cone of reduced luminance extending nearly 1,800 kilometers from the object's leading edge. It wasn't a tail. It wasn't a wake. It was a shadow, in the wrong direction. That single contradiction began a new chapter in the study of 3I Atlas. In standard physics, a shadow in front of a light-illuminated body can only exist if one of two things occurs. Light is being bent backward around the object, refracting through an uneven medium. The object is blocking non-visible energy coming from ahead and creating a negative imprint by disrupting a field we don't normally see. The first scenario, backward refraction, would require a dense, structured envelope of ionized gas ahead of 3I Atlas. But no forward-facing bow shock had been observed in infrared, UV, or radio. The area ahead was cold, undisturbed, and spectrally quiet. The second scenario was harder to explain. In early November, NASA's Solar and Heliospheric Observatory, SOHO, released passive coronagraph data showing a faint discontinuity in solar wind density just before the object's leading edge. For a span of nearly 20,000 kilometers, protons flowing from the sun were being diverted, not deflected like around a magnetic field, but nullified as if absorbed or screened. It wasn't a shadow of light, it was a shadow of force. Plasma physicists began to hypothesize the presence of a scalar gradient, a spatial zone where one or more background field strengths, electric, magnetic, gravitational, begin to cancel. These fields normally remain uniform at the scale of interplanetary motion, but near 3 I Atlas, something was different. Whatever the object was interacting with, it created a low-energy cone, not trailing, but projecting forward, as if anticipating pressure. Some likened it to the leading-edge shielding used in orbital re-entry vehicles to shape incoming force. A barrier formed not in reaction, but in preparation. Was this coincidence? A unique byproduct of its interstellar origin? Or was this object doing something no comet has ever done? Sensing the medium ahead of it and responding, others noticed more. When simulations were run using light from stars positioned behind the object's path, the forward cone also produced a measurable brightness suppression in distant starlight. Not lensing, not diffraction. A subtle dip like starlight was dimming as it entered the shadow zone, even though the object itself had not yet arrived. The forward shadow moved with the object. It held its shape. It pulsed. Ever so slightly, in sync with the 11.2-hour rhythm already seen in the jets, the heat rings and the radio echoes. It was part of a system. A comet has no system, no anticipation, no geometry that projects force ahead of motion. But this wasn't reacting, it was preparing. And in that quiet preparation, in that unnatural shape of absence, we may have caught our first glimpse of the object's intention. The first sign came not from what we saw, but from what we couldn't stop seeing. Most interstellar objects are dim. Even when passing close to the sun, their surfaces reflect only a small portion of incoming light. The dark, carbon-rich crusts of comets absorb most wavelengths, scattering the rest through a veil of dust and vapor. But 3I Atlas was bright, too bright. In mid-October, shortly after the Mars flyby, ground-based observers began noticing irregularities in its albedo, a measure of reflectivity. At first, it seemed like overexposure. The comet's coma was unusually crisp in long-exposure images, with edges more defined than expected. But the numbers didn't lie. Photometric studies showed that, across multiple bands from visible green to near-infrared, the object was reflecting nearly 64% of incoming solar radiation. For comparison, most comets reflect around 4 to 6%. Even freshly exposed ice doesn't exceed 25% under normal conditions. Only metallic surfaces or engineered coatings can reflect at the levels seen here. And the reflectivity wasn't coming from the coma, it was coming from beneath it. Using polarization filters, amateur astronomers in Chile captured a series of frames that showed a specular reflection, a glint not from scattered dust, but from a flat, stable surface embedded within the inner coma. This glint rotated at a predictable interval, reappearing every 11.2 hours, perfectly synced with the now familiar pulse cycle, observed in radio, infrared, and jet activity. The implication: there was a layer curved, reflective, and rotating beneath the gas and dust cloud. NASA's NEOWISE infrared telescope confirmed the anomaly days later. Thermal contrast scans revealed that while the coma emitted typical dust temperatures, a central structure was bouncing much colder light, consistent with high reflectivity and low absorption. In essence, it was reflecting heat away, rather than radiating it. That's not how natural surfaces behave. Even ice absorbs some heat. Dust traps infrared. This was rejecting energy. The working term became the high reflectivity layer. Spectroscopy revealed further surprises. When examined across visible and near-infrared spectra, the layer did not produce a typical absorption profile. Instead of dips in the graph where materials absorb specific wavelengths, the curve remained flat and clean, as if designed to avoid spectral tagging. It was a mirror with no fingerprint. Speculation grew. Some proposed exotic ices under high pressure. Others suggested silica aerogels or naturally formed iron-magnesium crystals. But none of these materials explain the uniformity or the rotational persistence. The layer appeared to maintain its reflectivity from all angles, regardless of phase, something only engineered surface typically achieve. And then came the Doppler test. Using radar data from Goldstone's Deep Space Communications Complex, astronomers bounced narrowband radar pings off the inner coma. The return signal came back stronger than expected, not diffused but sharply defined. The waveform even showed phase coherence, suggesting a smooth, continuous surface rather than a rough, fractured one. It echoed like a panel, it gleamed like polished alloy, and it rotated not wildly, but with precision. Observers began to notice that this high reflectivity might not be an accident, but a form of defensive camouflage. By bouncing incoming energy away and hiding in a spectrum-resistant field, the object could avoid passive detection methods, scatter active radar, and maintain thermal stealth. In effect, it was cloaked, not invisible. But cloaking implies intention, and intention implies design. Still, no one dared say it aloud. Theories were written in cautious language. Anomalous optical layer, non-standard reflectance profile, spectrally flat shell. But behind the academic restraint was a quiet admission. This surface wasn't just shiny, it was selectively visible. The high reflectivity layer turned 3I Atlas into something more than a comet, not just reflective, but evasive, not just rotating, but pulsing, not just cold, but controlled. And in that precision, in the way it caught and deflected light like a question we weren't meant to answer, it became clear we weren't just seeing it, it was choosing how to be seen. Interstellar objects are supposed to pass through the solar system just once. They arrive from deep space on steep hyperbolic paths, swing around the sun, and exit their trajectories flung outward forever by solar gravity. But in the case of 3I, Atlas, something subtle changed. The outbound arc flattened, its inclination dropped, its trajectory, once cleanly hyperbolic, began to bend. This alone sparked concern. But what came next sparked a theory. On November 3rd, a group of orbital analysts at Caltech began running long-term trajectory simulations based on the object's updated path. When accounting for the slight velocity loss after the Mars flyby and the unexpected vector drift logged during the solar perihelion, one model emerged that caught everyone off guard. 3. I-Atlas wasn't escaping, it was looping. The model showed a shallow arc, one that bent the object back toward the inner solar system, not on a stable orbit, but on what could only be described as a re-entry pattern. Not a full return, but a calculated pass that would bring it back within astronomical proximity of the ecliptic plane and Earth's orbit within a multi-year timeframe. This behavior had never been observed before, and it led to one of the most controversial hypotheses in the recent history of orbital dynamics, the re-entry arc theory. The theory proposed that 3I Atlas was not on a random escape trajectory from another star system, but was instead part of a cyclical path, a long, slow, deliberate loop through interstellar space, returning to the inner system at carefully calculated intervals. A return implies intent, and intent requires structure. Some researchers noted that the object's velocity was just below the threshold for solar escape, enough to enter, but not enough to break free cleanly. That's not typical for comets. Random interstellar objects tend to overshoot, never to be seen again. But 3I Atlas was hovering on the edge of orbital capture in the narrowest margin possible. That margin is what makes the theory viable. If its trajectory had been 0.02 degrees steeper, it would have escaped permanently. If its velocity had been 1.3% faster, it would never return. But neither occurred. Instead, the object slowed. It bent. It began to drift laterally in the solar gravitational well, not falling inward, not climbing out, but skimming across the slope in a motion too stable to be chance. More alarming was the angle of return. The new simulations showed that its projected path, once thought to lead away from the inner planets, would bring it back toward the Sun's Earth-aligned corridor within the next 7 years. And unlike typical comet returns, which approach from above or below the ecliptic, this arc was nearly flat, as if the object wanted to stay level, stay in plane, stay visible. ESA has not confirmed nor denied this model. NASA has not updated the public database with the re-entry arc parameters. But internal data from the JPL Horizon system now includes a footnote. Object status. Escape uncertain. Trajectory requires ongoing refinement. That language has never been used for an interstellar object. Some theorists went further. They proposed that 3I Atlas's course wasn't just looping but correcting, that its mid-course vector shifts seen after the Mars flyby and again near perihelion were not caused by outgassing, gravity or solar radiation. They were adjustments, navigational corrections. If true, the object may not simply be returning by coincidence. It may be programmed or designed to re-enter the inner system at specific times, from specific angles, perhaps in coordination with external forces we've yet to detect, or worse, in response to something already here. The re-entry arc theory remains a fringe hypothesis in academic circles, but among the quiet halls of orbital command centers, it is no longer dismissed. It is modeled. It is tracked, because if 3I Atlas is coming back, then the story is no longer about what it is. It's about why it's returning, and what it remembers. Heat tells a story. Every celestial object, no matter how distant or inert, emits thermal radiation. Whether from sunlight, internal friction, chemical reaction, or past collisions, the infrared glow of an object offers a quiet fingerprint, a way to study what lies beneath its surface and how it interacts with its environment. But 3I Atlas was quiet, too quiet. Beginning in late October, a network of infrared observatories, including the James Webb Space Telescope, the IRTF on Mauna Kea, and a series of passive sensors aboard ESA's Mars Express began releasing datasets centered on the interstellar object's heat signature. What they found was a suppression, not a cold region, not a shadow, but an absence. The thermal emissions from the nucleus of 3I Atlas were not just low, they were incomplete. Large sectors of the surface emitted no measurable heat at all, even under direct solar exposure. And the coma, usually vibrant in the mid-infrared due to excited particles, was strangely muted, showing a uniform, featureless profile. It was as if the object had gone thermally silent. This is not what comets do. Comets heat unevenly. They crack, pulse, and outgas in erratic waves. Their surfaces boil and rotate, producing jagged thermal patterns. Even in their quiet phases, natural objects leak heat. 3I Atlas did not. At a solar distance where most comets flare in brightness and begin shedding ice and rock, 3I Atlas remained inert. Its thermal signature, across multiple wavelengths, stayed flat. Even the known pulse cycle observed in radio, light, and plasma did not translate to heat variance. In short, something was happening, but it wasn't producing warmth. Infrared spectroscopists began to speculate. Perhaps the object's surface was coated in a high albedo reflective layer, similar to what had already been hinted at in radar data. Such a layer might bounce sunlight and delay heating. But even so, some absorption, and thus some re-radiation, should still occur. Others suggested a cryogenic core, so cold and dense that it absorbed heat without releasing it for hours, or even days. But again, this would eventually produce delayed emissions. That never happened. The most puzzling aspect came from comparisons between inbound and outbound data. Normally, as a comet recedes from the sun, its thermal profile changes. It cools. It fades. 3I Atlas did not cool. It simply stayed the same, like a body whose thermal state was being regulated not by nature, but by something akin to control. One working group in France explored a deeper possibility, that 3I Atlas was not emitting heat because it wasn't retaining any. That somehow, the object was acting as a thermal insulator, shedding all absorbed energy via non-radiative processes. In simple terms, the energy went in, but didn't come out. It didn't reflect. It didn't emit. It vanished. Some called this a calibration failure. Others, a sensor error. But when 3 different platforms, JWST, Mars Express, and an independent Chilean observatory all reported the same pattern, the term anomaly became insufficient. This wasn't noise, it was silence, and the silence was intentional, because in the quiet, there was a pattern. The same regions that failed to radiate heat were the same that produced the strongest plasma pulses, the same zones that deflected radar, the same surfaces that reflected light but not warmth, and that meant only one thing. Something aboard, or within, 3I Atlas was interacting with energy, but not like any comet ever recorded. It absorbed without re-emitting. It operated without heating. It pulsed without warming. In physics, thermal equilibrium is inevitable, unless something stops it. And if 3I Atlas has found a way to resist equilibrium to remain silent in heat even while active in force, then we are no longer watching a cold rock. We are watching a system that chooses when and how to be warm. And that silence might be the most deliberate signal of all. Human beings are wired to see patterns. It's one of our oldest survival traits, the ability to find structure in chaos, meaning in repetition. We see faces in clouds, shapes in stars, lines where there are only dots. In science, we call this pareidolia a false perception of order, a trick of the mind, but sometimes the pattern is real, and we notice. In late October, a wave of high-contrast amateur photographs began circulating online. Most were innocuous, long exposure shots of 3I Atlas, framed against the same starfields. But slowly, a few images began to catch attention not because of what they showed, but because of what repeated. In image after image, faint arcs near perfect curves traced through the coma. Not once, not randomly, but in sequences. Even more curiously, they appeared at regular intervals, spaced with angular precision, curving away from the object's core like concentric rings. The human eye noticed before the algorithms did, and once noticed, the question formed, is this geometry natural? At first, scientists were cautious. Comets can produce jet spirals, gas arcs, and pressure waves that form temporary curves, but those structures tend to be chaotic, scattered, and short-lived. The shapes around 3I Atlas were different. They persisted. They rotated in sync. They aligned with the pulse. Mathematicians at a small observatory in La Palma began mapping the arcs digitally, overlaying each image with a radial coordinate grid. What they discovered raised eyebrows. The arcs weren't random. They matched a logarithmic spiral, the same pattern found in Nautilus shells, hurricanes, and galaxies. A self-similar, scale-invariant structure. Other images showed even more unsettling details. At specific rotation angles, sharp lines intersected the spiral arcs, forming triangular intersections. In one frame, the reflection points on the surface plotted into a hexagonal grid, not exactly perfect, but too consistent for coincidence. Across multiple observation points in Finland, Argentina, Australia, the same geometric echoes repeated. And while pareidolia is always a possibility, scientists admit, the angle spacing between these arcs held within a tight 0.7 degree margin across 6 frames taken from different hemispheres. This is not how gas behaves. This is not how randomness looks. Some began comparing the structure to known antenna geometries, phased arrays, resonant plates, nested harmonics. Others proposed crystalline structures, internal lattices reflecting outward through the coma via light diffraction. But neither explanation accounts for the one fact nobody could ignore. The geometry rotated, and it rotated with intent. The 11.2-hour pulse cycle, already confirmed in thermal, radio, and light bands, seemed to control the phase exposure of the geometry, as if these shapes were not simply on the object, but part of a larger system that responded to position and angle. Pattern recognition software, normally used in satellite imaging, was applied next. When instructed to ignore known natural formations, the algorithms still flagged repeating symmetry, not from one frame, but across dozens. The software saw what humans saw, and that left us with a paradox. Was 3I Atlas merely looking artificial because we want to see patterns? Or was our brain, honed over 100,000 years of shape recognition, simply doing what it does best, noticing when something is designed? Because deep inside our minds, there's a threshold, a quiet alarm that says, this isn't chance. This was placed. No one has said it officially, but many have thought it. The patterns around 3I Atlas don't feel natural. They feel familiar, like something meant to be seen, by beings evolved to recognize intention in form. And if geometry is the language of the universe, then perhaps this object is speaking, quietly, repeatedly, and precisely.